Okay, so we take another look here at the Hull-White 2004 model for valuing or accounting for employee stock options. In the paper here, I've left a link to the original paper and also some other reference to Cython, Wiener, Zapatero 2008, who looked at change in accounting standards framework that encouraged fair value accounting. Now, key issue with the original Hull and White 2004 model is that it's very slow in terms of computation, a lot slower than a normal binomial tree that we would apply for valuing European options or American options. Part of the difficulty around the employee stock option framework set out by Hull and White is that there is a barrier embedded for early exercise. And that's a sensible condition, but it does produce nonlinearity in terms of the error. And it also creates a sort of a sawtooth convergence pattern where only at specific points and numbers of steps on the binomial do we actually reach convergence, but a lot of the time it drifts away. Now, this is not a pattern in terms of evaluation we observe with regular American options or European options, but when we see this problem arise, we've got to deal with it. The way you deal with it is you make sure the number of steps in the tree stretch out so that the touch or align exactly or as much as possible with the barrier specification set out in Hull-White. And once you take care of that problem, then you remove the sawtooth convergence problem. Other acceleration technologies that could be applied here to the binomial tree is that there are sections of the tree that, strictly speaking, we don't have to compute. So there's a zero section and an early exercise section that we might observe here. Just bring you to this graph here. So in terms of early exercise, these nodes, strictly speaking, don't have to be computed. So there's a whole section we could shear off from the binomial tree, and we would still produce the correct valuation for the option, even if we ignore these nodes. And there's a zero section in the tree. If we tear off or remove from the tree, it still will produce the same estimation for Hull-White, for the Hull and White 2004 model. So this type of truncation technology is applied. And also we make better use, instead of using static memory, we use dynamic memory as well. Now to achieve that, going back some time now, we have set this up initially in Hull and White, the Hull and White code in C++, and we can run the C++ code in Colab using percentage write file and main.cpp. When we execute that code, we can see it actually goes here into the content folder. Right, so just take a look here. Now, if I remove it, right, we can download it, take a look, or we could delete that file out for a moment. And then if I run the code again, what we observe is this main file comes across and sits here. And then to estimate the code with the truncation technology, dynamic memory, and Boyle-Lau specification, we use percentage script bash, and we output the results of our C++ code. The code executes quite quickly here, 0.23 seconds, which is actually quite fast, given the number of steps that we have here. And in part, that's happening because we're using C++, which is closer to the binary code of zeros and ones. So it's a more primitive in terms of proximity to the zeros and ones. That gives it a little bit of an advantage in terms of speed. Problem with running C++ in a Jupyter notebook, which is what Colab represents, it's difficult then for the C++ to kiss with other libraries in Python. So one possibility is to try and make use of the code in Python, but use faster computational libraries. And if we implement the same code again but using Python and the mat library, you can see the code runs reasonably well. It's at 5,000 steps. And the valuation that I get here, 2785 for these parameter inputs, aligns with the values we published in the paper on SSRN. Right, so if I was to bring the table up for a moment, you can see here at the 5,000 steps, using the parameter values as set out here, stock price, exercise, maturity, typically longer maturity dates and options, sigmas 20%, the risk-free rate's set at 6, vesting is 2, and the barrier is 1.5 times the exercise. And then the exit rate, or the churn, if you like, in terms of employees, is 4% per annum. When we take those parameter inputs and use Boyle-Lau, we get 2785, and that corresponds with the true value, which is a value we obtained from Svi Wiener a couple of years ago, supplied the true baseline values for our original paper, right? And we can see here with the Boyle-Lau specification, after 5,000 steps, we have a much more accurate result than just using whole-wide model without any enhancement, Boyle-Lau enhancement. Again, we can check the model without Boyle-Lau in the first snippet of code. Now, this is just textbook code that uses static memory and tends to be quite slow. So again, it's main. So it's changed this one here. Perhaps I should delete to show you a little bit the dynamic here. So I'll remove those files, delete file. And then we write file main CPP, and that gets passed into the content folder. And then we output the result. And you can see here the result for the whole white model without the Boyle-Lau specification is it's 2803, and it's actually a lot slower in terms of computation time, right? So that result is off. The true value 2785 for these parameter inputs. Whole white Boyle-Lau is 2785, much closer. The whole white model with no adjustment, suffering the sawtooth convergence, is out $28.03, which means we would probably need to take this up, 10,000, 20,000, maybe up as high as 100,000 steps, which is really impractical for the tree really to be converged. Okay, now taking that into account, we have code that is suboptimal, and we have code below here which is optimal based on Boyle. Phelan Boyle is an economist from actuary finance researcher from Ireland, and has made quite a significant contribution to the finance discipline in terms of the trinomial model, and also Monte Carlo as early as 1977, 1978. Phelan had developed Monte Carlo option valuation, which was pioneering back in the 70s, right? So we use the Boyle-Lau specification in our tree, we get an enhancement, and with the dynamic code, which is optimal, and with truncation, you can see that the speed of estimation is 0.23 seconds, and it's closer to true. Okay, the difficulty with using C++ in Colab is that it doesn't, when we set up our estimation, it doesn't link across then to graphing. There's not much graphing capability in terms of C++, and we would like to use libraries like matplotlib. So how do we get the speed, performance, and accuracy then in Python? Well, initially we set up the code so that it executes, and we use the mat library, but again, the same truncation, dynamic memory, Boyle-Lau specification is used here. And when we output using the same parameter inputs, when we output a result, we get 2785, which is correct. And when we look at the time it takes for execution, turns out to be quite slow, or not quite as fast as we would like. So in some respects, even though it's dynamic and there's truncation, Python sometimes presents issues in terms of its sluggishness in performing estimations. And that's a real, that can be a problem when you're trying to generate graphs. It just takes so long. So that took 3 seconds. In fact, it took 24 seconds, but we did 7 runs, 1 loop each, and they averaged out to be 3 seconds for the 3 seconds each time. Okay, so that's quite slow, but it is producing the correct result. If we use NumPy, which is another library in Python, it's optimized because NumPy generally is good for multi-array, multi-dimensional array type computation. And NumPy was developed, in fact, to solve a problem for Python, and that problem was the sluggishness of Python generally. And you can see here how we get a speed bump, we get a fairly dramatic improvement in speed. So it's 0.335 seconds, which is really fast, right? Or it's much faster than using the math library. And again, the same result. And then the final enhancement we use here is to use Cython. And Cython is a library in Python that allows us to connect or kiss with C speed, C level of performance. But then once we estimate our user-defined function here, our helper function, once we develop it, we sort of get C performance, right? And we run the model here. This is not a problem, right? We can input in the same parameter values as before, the 5,000 steps. Let's take a look. Do we get the right result? We get 2785 for these parameter inputs. That looks correct. And then we do a speed check to judge the performance of this Cython code. Now we're hoping it will be faster than NumPy, so that we're really taking advantage of the C performance, right? So before, when we used NumPy here, it was 335 milliseconds, and for math, the speed was 3 seconds, which is way, for the math library, takes a much longer time to execute the estimation. NumPy, we get a bump up in terms of speed performance. And with Cython here, when we come down and take a look at the speed performance, it's 199 milliseconds, which is a bit of an improvement over the NumPy library. Again, we get the same result, which is encouraging. And that means based on our Cython code here and the helper function we've developed, when it comes down to graphing, we can produce faster estimation, which is very useful in terms of performing parameter sensitivity when we change a particular parameter input. So what I would like to do here is to rerun the same binomial tree, the employee stock option whole white estimation using the Boyle-Lau optimization. I'm just doing it at the 100 steps, so not 5,000 steps. That obviously would save time as well. And we would also here are generating a range of stock prices. So we're considering the value of the employee stock option for, again, the same parameter inputs, but we're varying the stock price from 50 to 150 in steps of 20. So 20 separate estimations. And when we look at the output here, not too much latency, and we get the employee stock option parabola, something like the Black-Scholes parabola, right? And again, I leave a reference here to Svi because he did provide us with the baseline. Professor Svi Wiener from Jerusalem, And he did provide us with baseline true values for Hull White for the Hull White model. Okay, so let's leave it there.